What's up, guys? So today we are going to cover our oxidation reactions. And we're going to start with the oxidation of alcohols. So remember from the last video, we said that an organic molecule has been oxidized if it gains an oxygen or loses a pair of hydrogens. So when we oxidize an alcohol, we're going to lose a pair of hydrogens, one from the oxygen and one from the hydroxy-carrying carbon, and we're going to form a double bond. So that means our product of an alcohol oxidation reaction is going to be either an aldehyde or a ketone. So my first question for you is, can all alcohols be oxidized? Do all alcohols have a hydrogen attached to the hydroxy-carrying carbon? So I want you to think about that as we work through these examples today. Okay, so what reaction conditions do we need for an alcohol oxidation reaction? Well, we need an oxidizing agent, and in this class, we're going to use potassium dichromate, K2Cr2O7. And so like I said earlier, our initial product is going to be either an aldehyde or a ketone. If it's a ketone, the oxidation reaction is done. But if it's an aldehyde, that aldehyde is immediately going to be oxidized further into a carboxylic acid. So let's work through these three examples on this slide together, and then I'll have you try 3 examples on the next slide by yourself. Okay, so problem A here, we have a primary alcohol, methanol, and we're going to oxidize it with potassium dichromate. So we're going to remove the hydrogen attached to the oxygen and one of the hydrogens attached to the hydroxy-carrying carbon. And then we're going to form a double bond between our oxygen and carbon, and that is going to give us an aldehyde. And like I said earlier, when you have an aldehyde as your initial product, the reaction is going to continue, and that aldehyde is going to be immediately oxidized further into a carboxylic acid. So a primary alcohol will be oxidized into an aldehyde and then a carboxylic acid. Okay, so what about a secondary alcohol? So just like above, we're going to remove the hydrogen from our oxygen and remove a hydrogen from the hydroxy-carrying carbon. Then we're going to create a double bond between the carbon and oxygen, and that's going to give us a ketone. And remember, if our initial product is a ketone, then the reaction is complete. Okay, so what about a tertiary alcohol? So we can remove a hydrogen from the oxygen, but there aren't any hydrogens on our hydroxy-carrying carbon. So if we can't remove a pair of hydrogens, we cannot oxidize this alcohol. So there is no reaction when you attempt to react a tertiary alcohol with potassium dichromate. Okay, so let's try some examples. So I want you to pause this video and I want you to draw an alcohol oxidation reaction for each of these 3 alcohols listed on this slide. Okay, let's see what you came up with. So we'll start with 1-propanol. Okay, so just to make this a little easier, we'll draw in the implicit hydrogens on our hydroxy-carrying carbon. So when we oxidize 1-propanol, we have to get rid of the hydrogen attached to the oxygen and one of the hydrogens attached to the hydroxy-carrying carbon. And then we're going to create a double bond between our oxygen and hydroxy-carrying carbon. But this molecule is an aldehyde, so this molecule can be oxidized further. So this reaction is going to continue and create a carboxylic acid. Okay, so if you haven't already, go ahead and name your aldehyde product and your final carboxylic acid product. So our aldehyde product is propanal, and our carboxylic acid product is propanoic acid. Okay, let's see what you came up with for the oxidation of 2-propanol. Okay, so just like in the previous example, we'll go ahead and draw in any hydrogens attached to our hydroxy-carrying carbon. And in order to oxidize 2-propanol, we have to remove the hydrogen attached to the oxygen and the hydrogen attached to the hydroxy-carrying carbon. And then we're just going to create a double bond between our oxygen, and our hydroxy carrying carbon. And the name of this product is propanone. Okay, what about our last reaction, 2-methyl-2-propanol? So just like the previous two examples, we'll go ahead and add in any hydrogens attached to our hydroxy carrying carbon. And since our hydroxy carrying carbon is already making 4 bonds, that means there are no implicit hydrogens here. Therefore, there is no reaction when we attempt to oxidize 2-methyl-2-propanol. Okay, so our next reaction is thiol oxidation. So thiol oxidation requires a pair of thiols, and we're going to remove 1 hydrogen from each and then connect the sulfurs together. This reaction is going to require either Br2 or I2 as the oxidizing agent. And if we're going to connect the 2 sulfurs together, that means our product is a disulfide. Okay, let's try an example. So go ahead and pause this video and name your organic reactants, and then draw and name your organic product. Okay, so we have a pair of ethane thiol reactants, and we're going to remove a pair of hydrogens, 1 from each thiol group, and then we're just going to connect our sulfurs together to form diethyl disulfide. Okay, so we already hinted earlier that we can oxidize an aldehyde using potassium dichromate, but we can also oxidize an aldehyde using Benedict's reagent. So Benedict's reagent is an oxidizing agent that only works on aldehydes. It cannot oxidize an alcohol. And it's a mixture of copper 2+, which is our actual oxidizing agent, and sodium citrate, which is a relatively strong base. And it's been used to monitor for diabetes by testing urine for the presence of glucose. And as we'll see in the next module, glucose is a sugar that contains an aldehyde group. So the Benedict's reagent is going to start off blue because of the copper 2+. Then when it comes into contact with aldehydes like those found in glucose in urine, a redox reaction is going to occur. The aldehydes are going to be oxidized to carboxylic acids, while the copper 2+ gets reduced to copper 1+. And we're able to monitor this because you see a color change. So as you oxidize more and more of these aldehydes found in glucose, you're going to simultaneously reduce more and more of the copper 2+ to copper 1+, and the color is going to change from blue to orange. And we can use this color change to estimate the amount of glucose present in urine. Okay, so let's give this reaction a try. So I want you to pause this video, name our organic reactant, and then draw the oxidation product for this reaction. Okay, so we're starting out with an aldehyde. Our parent chain has 3 carbons, and we have a methyl group at position 2. So this molecule is 2-methyl-propanal. And when we oxidize 2-methyl-propanal, we should get a carboxylic acid, right? Well, let's see what we get. So we don't get 2-methyl-propanoic acid. We actually get 2-methyl-propanoate. So why do we get the conjugate base of our carboxylic acid? Well, remember, in addition to the copper 2+, Benedict's reagent contains sodium citrate, which is a relatively strong base. So as soon as our aldehyde is oxidized into a carboxylic acid, the citrate in solution is going to snag that proton, and we're going to be left with a carboxylate ion. So the final organic product when we oxidize 2-methyl-propanal with Benedict's reagent is 2-methyl-propanoate.